Okay, this is the practice test for MAC1140 Pre-Calculus. We're talking about the topics for exam 2, which are 5.1 through 5.6 and 5.8. Okay, the first video covered numbers 1 through 20. We are now on number 21. So again, this was under the instructions where a function is given and they want you to produce a graph of the inverse function. So all you have to do is pick some points that are on this curve. These are all points that are on the curve. -2, -6. -1, 1, that's a point on this curve. 0, 2 is on the curve, etc. So if you want to get the points that are on the inverse curve, then you just switch the x's and the y's, just like we did for number 20. Okay, so that would give us -6, -2, 1, -1, 2, 0, 3, 1, and 10, 2. Okay, so then plotting those points, -6, -2, 1, -1. So 1, -1, 2, 0, 3, 1. Oops. 3, 1 would be right here. And then, let's see, 10, 2. And then 10, 2. Okay. Make sure I have everything. So 1, -1, I have the 2, 0. I have the 3, 1, and I have the 10, 2. And so that would be this choice right here. Yeah, it can't possibly be that because the inverse has to have the same shape but a mirror image of the first graph that you had. So this turns right here. And that would be this choice right here. Okay, moving to number 22. Starting with this batch of problems, you're given a function, and this time they want you to find the inverse function. Okay, so the steps for this are, step 1, you're going to replace f of x with y. 2, you're going to switch the x and the y. And then step 3, solve for your new y. Okay, so completing those steps right here, taking the f of x and replacing with a y, I would have y is equal to 4x plus 3. Okay, then switching the x and the y, I would put an x here and a y in place of the x. Now we have a brand new y where the x used to be, and we're going to solve for that y. So we're going to move this 3 over here, at which point it would become -3. So now you'd have x minus 3 on the left and just a 4y on the right. You would then divide by 4 to isolate that y. Likewise on the other side, and this would end up being your inverse function, x minus 3 over 4. Once you solve for that new y, you will put the inverse symbol in place of it and copy the function the inverse function that you created. And that is the answer for number 22. So let's see, for 22, x minus 3 over 4. So that would be D, because D actually has the inverse symbol as well as the correct function. So for 22, that's D. Okay, number 23. I think I'm going to move over to the paper, though. So for problem number 23, we have f of x is equal to 5x squared plus 3, and then they make a comment here that x has to be greater than or equal to 0, and that's because the inverse doesn't exist unless that's true. So, following those same steps, replace the f of x with y. Okay, then you're going to switch the x and the y. So x here and a y right here. Okay, then you're going to bring this 3 over here. It's x minus 3. That leaves you with 5. Y squared is equal to x minus 3. Then trying to isolate for that y squared, we're going to divide by 5 on both sides. That'll leave you with y squared is equal to x minus 3 over 5. And then get rid of the square. And you're going to have y is equal to x minus 3 over 5. And that is your inverse. Put the inverse symbol in place of that new y that you've solved for and copy the inverse function that you've created over on the left side. For 23, that is going to be choice A. Square root of x minus 3 over 5. Okay, moving to 24. Problem number 24. Might have enough room on the paper here. So step 1, we're going to replace the f of x with y. So it'd be 3x plus 5 over 2. Then we're going to switch the x and the y. So it would be x where the y is and y where the x was. Okay, then we're going to solve for the new y. We're going to cross multiply first so that we don't have a fraction. So 2x is equal to 3y plus 5. Okay, then we're going to try to isolate for y. So we're going to bring this 5 over here. In other words, we're subtracting 5 from each side. And then we're going to completely isolate the y by dividing by 3 on each side. Okay, that would give us, in place of the y, we will put the inverse symbol. And then the inverse function that we got on the other side, 2x minus 5 over 3. Okay, and that would be, let's see, choice A. Okay, moving to number 25. In problem 25, 26, all the way through 29, we have some, actually all the way through 30, we have some graphs that we're taking a look at. A lot of these, some of these are going to just be, if you understand, you know, vertical, horizontal shifting and basic things like what flips it over the x-axis, that's when the negative is out front. So let's see if we can find anything like that. Like if there would, if you were to take, This is what the y to the 2x typically looks like. Because these are all some version of the exponential function where the base is 2 and the exponent is x. Well, that basic function typically looks like this. It goes right through 0, 1, because when you put a 0 in there, 2 to the 0 is 1. And then it skims along the x-axis. That's what it looks like. You know, not that I'm doing like exact points, but that's a key point that it goes through. And you can see that this does not go through 0, 1. In fact, it's 1 unit higher than it typically should be. So if you understand what makes a graph shift vertically up, it is this number out here. Vertical shifts, the way it's not the basic one, so it can't be that answer right there. Otherwise, it would have went through 0, 1. But when a graph shifts vertically up 1 unit from where it typically is, and again, it typically goes through 0, 1, yet the point that it turns at right here, rather than 0, 1, it's at 0, 2 in this graph. So they're saying pick the function that, you know, was responsible for that. This right here, let's see, it would be this one right here. Now you got to be careful here when you're looking at these functions, because this, you know, might be deceiving to you. This 1 is part of the exponent. That's why it's a little higher in the air than this one is. That would be a horizontal shift of -1. Because anytime you have a number mingled with the x expression, that's a horizontal shift. Horizontal shifts always behave the opposite of the sign that you're actually seeing in the function. This is a vertical shift, 1 down. Vertical shifts, you don't switch the sign. Exactly what you see there is what they actually do. This is a vertical shift, and it is 1 up. This is the one that was responsible for that graph, so the answer is C. You don't have to do a whole big table of values. You can use your calculator here as well. Okay, what you're seeing here, just like I explained, although they didn't have a parenthesis here, it would have been nice if it was printed as part of the test-generated question, but they didn't. So I like to have parentheses. You can always ask me if you're not sure whether it's part of the x expression. But this one, it's very clear that that -4 is part of the x expression. Anything with the x expression suggests a horizontal shift, and horizontal shifts always behave the opposite of the sign that you are seeing there on the number with the x. So that's a horizontal shift of +4. If it's horizontal, that means it can only be left or right movement. If we're doing a +4, that means we're moving to the right 4 spaces. And that's from where the graph usually is. If this would have just been y is equal to 5 to the x, regardless of what the base is, if there's no shifting going on, regardless of whether the base is a 5 or whether it's a 2, it goes through that key point 0. We put a 0 there. 5 to the 0 is 1. It goes through that point 0, 1. So you can kind of judge from there. Okay, so you can kind of, you know, make some decisions based on that about what you're supposed to do with this graph. Now, you can make a table of values here. You can get help from your calculator if it happens to be, you know, multiple choice, but you're going to have to show some work here. So let's say that, you know, you want to do transformations. You want to work off of the basic graph to get the real graph. If that's the case, which I have gone over in class, here are some points on the basic graph. You would have 0, 1, you know, and you can just make like a little table of values right here, or you can just write them without the table. It doesn't really matter. So I put 0 in there. Nice point to put would be -1. If you put a -1 in there, and you can use your calculator, you would get 1/5. 5 to the -1 is the same thing as 1/5. If you were to put a +1 in there, that's really easy to do. 5 to the 1 is just 5. So I'm going to just make a little graph of what the basic y equal to 5 to the x graph would look like. You'd have a point there at 0, 1. You'd have a point at -1, 1/5, just a hair above the x-axis. You'd have a point at 1, 5. So this is what the parent graph would look like. The unaltered, unshifted graph, it would look like that. However, if you do want to take these points that were so easy to calculate even without a calculator and build upon those to get this graph, then this is how you do it. Okay, you think about the fact that you're dealing with points that are going to go 4 spaces to the right. If it's a horizontal shift, it is something that is being done to the x's. So basically, what you're going to do is take any of the x values that you have here and just add 4. Because remember, if you're going to act out what is being suggested in this equation, you have to understand that that's a horizontal shift and they behave the opposite of what you're seeing in the equation when you're going to build points for the graph. So you're seeing a -4, that's really a +4 horizontal shift. So take those x's that we have right here and build some new points. And you'll be able to graph it. So take this x, add 4, but the y coordinate, that y partner stays the same. Take this x and add 4. That would give you 3. The y partner stays the same. You are only impacting the x's when you're doing a horizontal shift. Take this x value and add 4. You would have 5 while the y partner stays the same. So the real graph here would be, let's see, 4, 1. Right, 1, 2, 3, 4, 4, 1. And that's basically this point right here shifting 4 units to the right. The whole rest of it is going to look just like this graph. So then you're going to plot, let's see, 3 1/5. So 1, 2, 3, up a hair. And then we're going to go 5, 5, 4, 5, and then go all the way up to 5. Got the same shift, it's just that the whole graph shifts over 4 units. Still has an asymptote, this still hovers right above the x-axis. So they're also asking you for domain and range on this graph. So the domain is, this is a graph that goes all the way to -infinity. And this leg, I know it looks like it shoots upward, but it actually spans out. It actually gets wider and wider the more points that you plot on the graph. So this is actually said to go out to +infinity. All the exponential graphs are like that. They go from -infinity to infinity on the domain. So that's your domain. And then as far as the range goes, so domain is how wide the graph is. It goes as wide as -infinity and as wide as +infinity. When you're talking about the range, then you're talking about the y values suggested by the graph. The y values on this graph are all above 0. So 0 to infinity. Okay, so now you want to just pick a graph that looks like this graph right here, shifted over 4 units to the right, and has the correct domain and range. Let's see. I don't even see a graph here. Oh, there is one right here, but it's so light that you actually can't see it. Let's see for numbers. Yeah, I think it, I mean, it looks like there's a piece of it right here. It's just really light. That's not the answer, though. It doesn't even go in that direction. This looks like the graph right here, because remember, there was a point on the parent graph here, but then the whole graph shifted. So this is 1, 2, 3, 4 units over. This is the actual answer. You can't see the tail that is like right above the x-axis, but that is there. It doesn't come out so good on these test-generated tests. So let's see. Domain's correct. Range is correct. This is the graph, which I could tell from the shift. Okay, couldn't have been that one. Here, I know you can't see it, but it's a graph that looks like this. That wasn't the graph either. So Answer was B. Okay, this one. What is happening with this one? Well, there is a horizontal shift of positive 3. What does that mean? That you're going to take the x's on the parent graph and add 3 to each of them. So this is a horizontal shift right there inside the parenthesis, while this free loose number, this constant, that's a vertical shift. Vertical shifts behave exactly as they seem to. This is a positive 2, so your vertical shift is actually going to be positive 2. Vertical means up and down. Therefore, it is a move that you make. It is something that you do to your y values. You're going to take your y's and add 2. So what you should do is just what I did for problem number 26. Think about this without all the extra shifts that are written here, like the horizontal and the vertical. Just think of it as 3 to the x. Get some points for something simple like that, the parent graph. Very simple to just plug in a 0, a negative 1, and a 1 to get some real basic points. Okay, if you put a 0 in there, anything to the 0 power is 1. If you put a negative 1 in there, it would be 3 to the negative 1. If you put a negative 1 in there, that's the same thing as 1 over 3 to the positive 1. A negative exponent means this base is happening down in the denominator, but now the power is positive. That's how you rewrite a negative exponent as a positive exponent. So you should be able to do that just in your head, just by knowing what negative exponents mean. If you put a 1 right there, 3 to the 1 is just 3. And with these basic points, you can also get the new graph. Y is equal to 3 to the x minus 3. You don't need to plug into this. That would be really hard to plug anything. It's not like it would be really hard, but it'd be a lot more work than just realizing, hey, if I know how to read the commands, which is what we were talking about right here, then I know what simple moves to do to either the x's or the y's or both. There just happens to be a vertical shift and a horizontal shift. That's your horizontal shift. This is your vertical shift. And just adding things and subtracting things in this way is much easier than plugging into that. Because then you got to get you're probably going to have to get your calculator involved. So then all you have to do is take these 3 points. Why don't we do the x's first, and then we'll do the y's. We are adding 3 to each of the x's. So 0 with 3 added is 3. Negative 1 with 3 added is 2. 1 with 3 added is 4. So I just did this horizontal shift to every single one of my x's on the parent graph. Then as far as the y's, I'm adding 2 to each of these y values. So this would become a 3. This would become 2 1/3. And this would become 5. Adding 2 to each of my parent y values. So when I go to plot my brand new graph, it's 3, 3. So 3, 1, 2, 3. It's 2, and then 2 1/3, and then there's 4, 5. 4, 5. Okay, now before I draw this, I want to talk to you about the asymptote. Do you see that this graph is shifted vertically 2 units up? You're shifting the whole graph 2 units up. If this had no vertical shift at all, it would be a graph that went right through 0. It would go right through 0, 1, and the tail would hover above the x-axis. But instead of hovering above this x-axis, we're taking the whole thing. This x-axis serves as the asymptote. So if this entire graph is shifting 2 units up, so is the asymptote that it typically obeys. It typically uses this x-axis for an asymptote. We'll draw a horizontal line just like this, but 2 units up. So this will play the new role of the horizontal asymptote. Because that horizontal asymptote is shifting 2 units up, the whole graph shifts 2 units up because the horizontal asymptote is what holds it up. Okay, so that's your new graph. You can also tell the domain and the range. Domain for all of these exponential graphs, negative infinity to infinity, but the range is controlled by the asymptote. So all the y values on this graph are above 2. Okay, this brand new line is up at a height of y equal to 2. So 2 to infinity is where you will find your y values on the graph. So let's pick the correct graph. And I don't think they asked the domain and range here, but so I answered it anyway. Okay, so all we're looking for is the correct graph for 27. All right, so let's take a look at these. This is shifted too far to the left. This is too low. This one is the one that's the answer because this is 2 units higher. It's obeying an asymptote where the whole thing is above 2. So this is your answer. That's too low. Okay, moving to this. Now, you also have to know what happens when you multiply certain things by negative. When you multiply the x's by -1, it flips the graph over the y-axis. Whereas if the negative multiplier would have been out here in front of the base, it would have flipped it over the y-axis. So you have to think about, you know, what it usually looks like. Again, if it was just y equal to 2 to the x, it would go right through 0, 1. It would look like this, like that. If you're going to flip this over the y-axis, then instead of it going this way, it would go this way. Still with the tail fluttering above it. But then there's something else going on here. So this is just, what I did right here is just flipping over the y-axis, flipping across the y-axis. If you take this graph right here, this basic graph right here of the parent graph, and just flip it across the y-axis, it would go up this way and have the hovering tail above the x-axis. But however, this is a vertical shift. It's a vertical shift that goes down 1 unit. So not only is this thing flipping across the y-axis, you're also going to pull it down, and instead of that asymptote being the x-axis, it's going to be that new horizontal asymptote is now going to be down here, but going in this direction. So this is really going to be, and everything's going to come down. So this point right here, where it went through 0, 1, it'll be 1 unit lower than that. It'll still go in this same direction so that you're having that flip over the y-axis, but it'll obey a new horizontal asymptote. So this is what it would look like even without doing a table. You have this new horizontal asymptote of y equal to -1. It's flipped across the y-axis, which yanks all of the points down as well as the horizontal asymptote. So that particular graph that, you know, corresponds to all of that, this is too high because it should be going through 0, 0, not 0, 1. This going in the wrong direction. And this is it right here. See, goes through 0, 0, flipped, and it is obeying a horizontal asymptote that is 1 lower than the x-axis, and still going through 0, 0, flipping over that y-axis. Okay, so that would be C. Okay, then you come to number 29. What we talked about in the guided notes is that whenever you have a base where the top is less than the bottom, numerator is less than the denominator for, an exponential function, what happens is that instead of it going like this, it goes in the opposite direction. It still goes through 0, 1, but in the opposite direction. Now, this particular graph does not have any shifts. It's not horizontally shifted or vertically shifted or flipped or anything like this. It just goes in the opposite direction. So rather than going like this is for when your base is bigger than 1. See this base of 2, as we have looked at in a couple of problems in this practice test, when your base is bigger than 1, it's going to go in this direction. But as soon as you start getting into stuff like this, where you have a base, the top is less than the bottom, numerator less than the bottom, it switches the direction. It still has that key point right there of going through 0, 1. Still uses the x-axis as the horizontal asymptote, but it goes in the opposite direction. So remember that when the base is in between 0 and 1, that's when it's going to go off in that direction. So let's see. Wrong picture. 29. Wrong direction. This is it right here. And again, you could use your calculator if you need help with these. But, I would love for you to just understand the basics of, at this point, you've seen it enough in other classes where you should know the basic mechanics of what takes a graph and shifts it left or right, horizontal shift, and what takes, where do you find numbers that move it up or down. You should know those kind of things. So this one, e to the x plus 3, okay, this base is bigger than 1. You got a base here that's greater than 1. Anytime your base is greater than 1, it's an increasing graph. It goes through 0, 1, and it's going to climb upward and to the right. Okay, however, this happens to have even though they don't have this in parentheses, this is mingled with the x. It's up in the exponent part of the exponent. So this one happens to have a horizontal shift. Now, I know you're seeing a positive 3 there, but horizontal shifts behave the opposite of what they appear to be doing in the equation. When it comes to graphing purposes, you must switch that sign. So we have a horizontal shift of -3. So you might be able to pick the graph just by understanding that typically the graph goes through this point right here, but you're going to shift it 3 units to the right. So instead of it going through there, that turning point is going to be right here. It's still going to flutter along the x-axis and then climb upward. Now let's see if that's enough to pick the graph, because if we need to fine-tune this graph, then we will. Okay, so this is, a student will pick this if they don't realize the thing about anytime it's a horizontal shift, it's the opposite of what you're seeing here. The graph should be shifted this way. This one is shifted to the right. So this one is shifted in the wrong direction. Okay, this one is shifted to the left, and let's see if it looks like it is shifted 3 units to the right. Yeah, that looks like it, because this turning point is 1, 2, 3. Yep, here it is right there. So this is the actual graph. That is not shifted at all because it's still going through 0, 1. That should have been shifted over here, and this is too high. It did not have a vertical shift. It had only a horizontal shift. Okay, so now we come to these problems where we are solving equations. So I'll see how much of it I can fit here, and if not, I'll move to paper. I think I'm going to just do it on the paper anyway, so let's spread out a little bit. Okay, so problem 31. Okay, so we have 2 raised up to a power of 3x minus 5 is equal to 16. So we can go 2 and leave this as 3x minus 5. And we want to use the same base here if we can, because remember, 2 exponential expressions are equal only if their bases and their powers are equal. Well, this put in base power form is 2 to the 4th. You can see that the bases are already the same. So for these to be completely equal to each other, these have to be equal as well. So then the problem breaks off into you working with just the exponents. So it's 3x minus 5 is equal to 4. Bring this over here, and you would have 3x equal to 9. Divide by 3, divide by 3, and you would have x equal to 3. Okay, so number 31 is C. Okay, moving on to number 32. Sorry. I don't know if you saw all of that or not. So I started off with 2 to the 3x minus 5 equal to 16. I wrote both sides using like bases. Once the bases are the same, you can work just with the exponents, which is what I was doing right here. 3x minus 5 equal to 4. I solved and I got 3, and that was C. Okay, moving to 32. In problem 32, we have 9 raised up to a power of 2x times 27 raised up to a power of 3 minus x is equal to 1/9. Okay, let's see what we can do with this. It's a little bit more complicated. I'm thinking of going bases of 3 because I can't really do anything with this unless the bases are the same. So I'm going to go 3 squared for my 9. That 9 already had a base of 2x. So I can call this 3 to the power to a power. You multiply the powers when you want to raise one power to another power. So this power on the 3 would become 4x. Likewise, I'm going to do something similar here. 27 is the same thing as 3 to the 3rd, but that 27 already had a base of 3 minus x. Now I'm going to mingle this power with this power by using the power to a power rule and just multiplying this power with this to mingle the two powers together. So let's see. 3 times 3 is 9. 3 times negative x is negative 3x. Now I can do something with these. If you are multiplying two bases, multiplying like bases, you add the powers. Just add the exponents, powers, whatever you want to call them. So this would be 3. I'm adding those powers, 4x plus 9 minus 3x, and getting a new power of 4x minus 3x is x plus 9. And then over here, since I'm going all bases of 3, I'm going to go 1 over 9 is the same thing as 1 over 3 squared. And that's the same thing as 3 to the negative 2 while having 3 to the x plus 9 here. So this is x plus 9 now. Now that I have the bases the same, I can work just with the exponents. So this would be x plus 9 is equal to negative 2. And then to complete the solving of this, you would move the 9 to the other side, at which point it would be negative 9, and you would get negative 11. So for number 32, that answer would be D. Okay, moving on to 33. Uh, 33, 16 to a power of x plus 1. And then over here it's 2/4 to a power of x minus 1. And we're trying to work towards, getting these bases to be the same if we can. I think I'm going to go, I think there's some promise in using a base of 2, even though this can be written with a base of 2 or 4. What I'm looking at over here, which is giving me the idea of which of those two bases to use, is that this is really 1/2. And 1/2 is the same thing as 2 to a power of negative 1. It's 2 to the 1 when it's down here in the denominator, but if you're going to write it in non-fractional form, then this 2 comes up here and you have to express the exponent as a negative exponent to, signify that it came from the denominator. So see, I got a base here, and I can mingle this power with this power by just multiplying this negative 1 times that. You're raising a power to a power. You have to multiply them, so it would just be negative x, and then negative 1 times negative 1 is positive 1. So that would be my new power. And since I knew I was going to be able to use a base of 2 here, then I should be using a base of 2 here. So this is 2 to the 4th for the 16, which already had a power of x plus 1, and again I'm doing power to a power, so I'm multiplying this power with this power to mingle them into one power, so that would be 2 to the 4x plus 4. Okay, so now we finally have two exponential expressions where the bases are the same, and again, once you get these bases to be the same, you can work just with the exponents. So we break off into the exponent on the left. 4x plus 4 is equal to the exponent on the right. If you want these to be completely equal, they can only be equal if their bases as well as their exponents are equal. And we're trying to find out what makes them equal. So if you get all the x's on one side, you add x, and you would have 5x. Get all the constants on the same side, which would make this a negative 4. And you would have 1 take away 4, negative 3. Divide by 5, divide by 5. And you have x is equal to negative 3 fifths. Okay, and so 33 is C. Oops, tearing this place up. Okay, moving to 34, you have 2 to the x squared minus 3 is equal to 64. So I'm just going to go C. 2 raised to a power of 6. See, that's 64. So I can write the 64 as 2 to a power of 6. Well, this is 2 to a power of x squared minus 3. Bases are the same. So now I can work solely with the exponents. x squared minus 3 is equal to 6. Just using the exponents at that point once you get the bases to be the same. All right. If I'm going to solve for x squared, I'm going to have to isolate that term. I mean, I could bring this over here and then factor, or you can just solve it. You have options here. You could either bring this over here, you'd have x squared minus 9, factor it and get the two solutions, or you can bring this over here, have x squared equal to 9, and then just use the square root property. Take the square root of both sides, and don't forget, report both roots. So x is positive or negative 3. Okay, and so for 34, that would be B. Okay. Okay, going on to 35, find just, a typical application problem for doing interest problems. So it says find the amount in the savings account at the end of 9 years. So that's going to be your T value. If the amount originally deposited is $9,000, this is P in the formula that you're seeing down here. Interest rate, never use it as a percent, use it as a decimal. Slide the decimal 2 places to the left. It's at the end when you don't see a decimal. So use the decimal version. That'll be R, your rate. And then when it says it's compounded semi-annually, the N that you're seeing there as well as there, that's the number of compounding periods. In other words, how often do they go into your account and pay you interest? Well, if they're doing it semi-annually, that means twice a year. Okay, so now plugging into this formula, and again, the question was find the amount. That means the final amount in your account. So A is equal to 9,000 for P times 1 plus the rate divided by N, which is 2, raised up to a power of 2 times T. Number of years is 9, so that goes right in there. You're going to want to clean this up a little bit. So go 0.07 divided by 2 and add 1 to it. 0.07 divided by 2, add 1, and you get 1.035. And then the power is 18. Now put it in the calculator. Be easier if you clean it up a bit. Okay, so 9,000 times 1.035 raised up to a power of 18, I believe it was. And that would be $16,717.40. Okay, so right there. Okay, moving on to number 36. Okay, so let's see what we have here. It says a city is growing at a rate of 0.5% annually. If there were 2,806,000 residents in the city in 1995, find how many to the nearest 10,000 were living in that city in the year 2000. Use the equation y is equal to 2,806,000 times 2.7 raised to a power of 0.005. That was the 0.5% times t. Okay, so they've given us the equation. Okay. All right, so if we start plugging in here, it would be 2.7. This would just be 0.005. And the amount of time here, well, it says in this problem there was this many residents in the city in 1995, and they're asking us how many there would be in the year 2000. 96, 97, 98, 99, 2000, 5 years, or just subtract it and just do it in your head. Okay, so we're going to be putting in 5 for t, because t is the number of years. So we put that right in there. You might want to get that ahead of time. 0.005 times 5 is 0.025. Okay, and then just plug it in your calculator. So it's 2806,000 times 2.7 raised up to a power of 0.025. Oops, missed the number. 2806,000 times 2.7 for the base raised up to a power of 0.025. And that is, now let's see, we were supposed to round to nearest 10 thousandths. Nearest 10,000. Okay, so this is the so yeah, 36 would be D. So this would be to the nearest 10,000. 2880,000. Okay, so that is choice D. Okay, then moving to 36. In 36 it says the function d of h is equal to 5 times e to the negative 0.4 times h. That's the function that we're using. Can be used to determine the number of milligrams D of a certain drug in a patient's bloodstream 8 hours after the drug has been given. How many milligrams rounded to 2 decimal places will be present after 7 hours? So all you have to do is put 7 in there. I'm just going to put 7 right in there. You might want to get that ahead of time. This 0.4 times 7 is 2.8. This is negative 2.8 that we're going to be raising this e to. So 5 times e raised to a power of negative. All right, so 5 times second function, call up the e, which is in the first column. It's a second function, and raise it to a power of negative 2.8. Close that up, and you get 0.30405. And once again, they're asking us to round it to 2 decimal places. So that would be 0.30. We're going to cut it off right there. This number is not strong enough to round it up, so it's just 0.30 or 0.3, same thing. Okay, and that would be choice A. Okay, moving on to 37. In problem 37, it's asking you to, I don't know if we need to write this out on paper, it's not too much work for problems like this. Change the logarithmic expression to an equivalent expression involving an exponent. So this would be, if you're going to go into exponential form, this base that's hanging off of the log, it's going to be the base of your exponential expression. So it's the base. You go to the other side to go and grab that number that's by itself. It becomes the exponent, and this 1/9 jumps out in its place. And it's true. 3 to the power of -2 is the same thing as 1/9, because 1/9 is 3 over 3, is 1 over 3 squared. That's the same thing as 3 to the -2. Well, that would be choice A for number 38. Which number is this? So 37, we said was A. 38 is A. 39, if I want to put this in exponential form, take that base. It'll be the base of your exponential expression. Go to the opposite side to grab the exponent. And then it's basically these two switch sides. Okay, so that's your exponential expression. B squared is equal to 25. And let's see. For 40, it's just going to be the base on any ln expression is e. So take that base, go grab this number, which will play the role of the exponent, and then the x jumps over and takes its place. So these switch places. This comes over here. The x comes over here. Okay, so e to the 6 is equal to x. That's going to be b. So 39 is C and 40 is b. Okay, then moving to 41 through 44, all of the instructions are find the exact value of the logarithmic expression. So you can do all of these, I believe, with the inverse property. And that inverse property is one of the properties that we learned. It says that whenever you're doing a log or an ln, if the argument matches the base. So let's just say this was some value and this matches it. Then whatever's in the exponential position, the value that's in the exponential position, I'll just put an A there, is what this is equal to. So when this matches this, they cancel, they take the word log with it, and whatever's in this position is what this entire thing is equivalent to. So that's what I'm going to go for here. I'm going to rewrite this as log of base 7, and because I have a base 7 here, I want to try and write this using 7 to some power, because if I can get this base and my argument, which is right here on this level, to match, then they cancel. So let's see. 7 to the 3rd power is 343. That's it right there. 7 raised up to the 3rd power. And let's see, this 343, see how it's happening in the denominator? So I want to signify that it was happening in the denominator by using a -3 exponent. And when you get this to match this, they cancel, they take the log with it, and this is equal to -3. So that's B for number 41. And then for 42, I want to try and rewrite this 1, the number 1, using a base of 8, because then I can apply the inverse property. So this is the same thing as log base 8. Anything to the 0 power is 1. So I can rewrite the number 1 as 8 to the 0, 7 to the 0, 10 to the 0. I just happen to want to use 8 to the 0 because this base is 8. Now because this argument matches this base, they cancel, they take the word log with it, and this is equal to whatever is in that exponential position. That is A. In 43, I'm going to use that inverse property again. It is used a lot in solving equations. So this is log of base 9, and this, written in exponential form, is 9 to the, square roots are written like this, 1/2. You have 1, 9, that's where that 1 came from, and the index is 2. Okay, so this cancels with this, argument cancels it, take the log with it, and this is equal to 1/2, so D. Okay, last one on this video is going to be number 44. The base on any kind of natural log problem is E. So this argument matches the base, takes the log with it, I can't talk, whether it's log or natural log, and whatever's in this exponential position is what it is equivalent to. So that would be D. Okay, so that was numbers 21 through 44, and I will continue with numbers 45 in the next video.